Okay, so I can see there's been some conversation in the chat. So I'll just go through this briefly, and then we can get on to onto actual MPI. So I'll skip the actual rules because it's not particularly important here. So this was the pseudocode, and as I think you know, as illustrated in the animation I gave, the important point here, and as someone has pointed it out in the chat, that you basically want to divide the road up into small pieces. So if you have P processes, then instead of having N cells in each process, you have N over P, or each process is responsible for N over P. So the first parallelization strategy, which you might think of, so I've got an example here. I've got a road where I've got 8 cells, and I've just got 1, 2, 3, 4, 5 cars, just an example road. One thing you might do is you might say, well, why don't I just broadcast the entire data to 2 processes? Basically, I'll just send the entire data to 2 processes. So every process has a copy of the entire data, okay? And then I say, well, I split the calculation between the 2 processes. So the first process is responsible for the first part of the calculation, the second process is responsible for the second part, and they update that part. Well, this is called a replicated data strategy. And although it works functionally, it's not a good idea for 2 reasons. First, so in a replicated data strategy, every process stores the entire state of the calculation, but only is responsible for updating a subsection of it. And the reason that doesn't work is, first of all, having updated a subsection of the data, you have to resynchronize the data. So in general, maybe not in this particular example, but in general, you have a global resynchronization. So it does ridiculous amounts of communications. But also, it's not good in terms of memory. What you're saying here is that every process has to store the entire state of the road. And that means, I often say the only reason you do parallel programming is to make things go faster, but you also benefit, as somebody already pointed out, from lots of memory. And here you don't benefit from having a lot of memory, because you have to, the entire calculation would have to fit on a single process. So that's not really a sensible strategy. The obvious one to do is to do a parallelization strategy. You scatter the data between 2 processes, distributed data strategy. Internal cells can be updated independently, but you need to communicate the neighboring processes. An important point when we thought about the people phoning each other, they only needed to tell each other what was happening on the boundaries. And this is actually quite typical of scientific and technical codes, that you often have nearest neighbor communications, like you do in this traffic model. Say you had a problem which came from discretizing a partial differential equation. That's quite standard, and so you only have to communicate boundary data. So you split the calculation between 2 processes, and each process must know which part of the roadway it's updating, and you synchronize the completion of each iteration and attain the total number of moves. So by communicating the boundary data, we can make sure we can do the calculation correctly, but each process only knows how many cars have moved on its particular subset of the road. So we need to do a reduction operation to work out the total number of moves. So parallelization, load balance is not an issue. Updates to equal computation in my naive approach. So they split the road into equal cells of size N over P. For each piece, the important point is that the rule for cell I depends on your neighbors I minus 1 and I plus 2 and I plus 1. So actually, if you have 1,000 cells, the interior 998 can be updated independently. You don't need to communicate with your neighbors, but the edge cells have to be, the edge cells are updated by other processes. You have to communicate the boundary information. So the communications is twofold: one, to get values of the edge cells from the other processors, and also produce a global sum of the number of cars that move, and also actually begin and end to distribute and gather the road, if you want to consider that step. So what you do is you, so what we want to do is we want to take this road, and this is the correct answer, where this car moves, and this car moves, okay? So what we've done is we've added 2 processes, and we also add 2 halos. These are called halo or ghost cells, which we add on the end. Now, the reason this makes parallelization simple is in the serial code, we just use them to a copy. In the parallel code, we use them to store the boundary data, okay? So actually in both codes we use them to store the boundary data. It just happens in the serial code the boundary data was just a local copy. In the parallel code the boundary data comes from your neighboring processes. Okay. So so what we have to do, we copy data tables. So it's I've only got thinking about two processes here. The diagram doesn't look particularly good. But we have to take that data to there, that data to there, that data to there, and that data to there. So now every process has a copy of its local data and the data of its neighbors, which is stored in these halos. And then we can just run the same code, actually exactly the same code, to update the interior cells. And then, so the first one has one move, the second one has two moves. And then actually there's another communication step where we have to communicate the data to get the total number of moves of 3. And so that's what we're going to do. But the subtleties were, right. So if you do synchronous send, okay, someone's pointed out you get deadlock because the two processes example doesn't work very well. Let's think about 10 processes, okay? If everybody issues synchronous send, everybody is sending to their neighbor. So process 1 is sending to 2, 2 to 3, 3 to 4, 4 to 5. And importantly, the end process 10 is sending back to the first process. So everybody is phoning. Remember, synchronous send doesn't complete until the receive is issued. But if everybody is phoning, everyone's thinking, why is the phone engaged? Because everybody is phoning at the same time, okay? So in this case, if you issued the receives first, everybody will be doing a receive and there will be no sends. So if you do synchronous send, you have deadlock, okay? It's like everybody phoning their neighbor at the same time. You're bound to get deadlock. So if you do asynchronous send, it's actually much simpler. You can issue the send. It's like posting an email, posting a letter or sending an email. Then you can issue the receive from your down neighbor, and that matches the send from your down neighbor. And then you can do the opposite one. You can issue a send to your down neighbor and issue a receive which comes from your up neighbor. Okay. So there's a comment here that it would be much easier if it's asynchronous. Yes, communication would be much easier if it was always asynchronous. We'll see in MPI though that's quite difficult to arrange. So actually in MPI, one of the difficulties, and it's slightly subtle, but it is an important point, is that you have to write programs typically which cope with synchronous send, and then you get a problem here. Now, there's actually a simple bit of a hack here to get synchronous sends to work. You can break the processes down into two groups, even groups and odd groups. The even processes are 2, 4, 6, 8, and the odd ones are 1, 3, 5, and 1, 3, 5, 7. 2, 4, 6, 8, 10, 1, 3, 5, 7, 9. If the even process is send first and the odd process is receive first, then the odd process, you can match them up, okay? So you can do that for simple cases, but in general, that doesn't generalize. So it's actually a bit of a subtle point in MPI. It's unfortunate we have to think about this early on, but it is important to understand. The most important thing I think to think about this exercise is you need to understand if you implement this with synchronous communications and you don't do something clever, like split them into odd and even groups, you are going to get deadlock. Whether you issue the send first or the receive first, it doesn't matter. If you own the sends, there's no receives. If you issue all the receives, there's no sends. And if the send is synchronous, that will give you deadlock. And it'll come back to why that is. Whoever made the comment here is right. It would be simpler if we had asynchronous sends, but we don't. Sorry, typically we don't. So hopefully that was useful. I realized, so I'm now going to give, if there's no more questions, I'm just going to give the first lecture, which talked a bit about actual MPI. So I'm going to give a brief overview of MPI and give a very few basic MPI calls, and then we will actually write some simple programs. So what is MPI? Well, MPI was designed back in the mid-90s, started in 93, and it was the first message passing interface standard. What happened is parallel computing had been around since the mid to late 80s. But what happened was every time you got a new parallel computer, it had a different message passing library, which was a nightmare. So after about 5 or 10 years, people got bored with this and said, let's define a standard. And the good thing about the MPI standard was it was in some senses best of breed. It was based on a lot of other attempts to do something so people knew what worked and what didn't work. There were 60 people involved, including EPCC. Both users and vendors were represented, which is very important. It was an international operation. So MPI is a library of functions or subroutine calls, not a language. There's no such thing as an MPI compiler. Okay, there is no such thing as an MPI compiler. Now, the way MPI is implemented, that's slightly obscured, but there isn't such a thing as an MPI. It's not a language, it's a library. The C or Fortran program compiler you invoke knows not what MPI actually does. Okay. Goals of MPI provide source code portability to allow efficient implementation. Source code portability means that if I write a correct MPI, just if I adhere to the C or C++ or Fortran standard, if I can run that program using the GNU compilers on my laptop, it should also run correctly using the Cray compilers on a Cray. The same thing with MPI. If I write correct MPI code, I can develop an MPI program which runs on my laptop, which also runs on any parallel computer in the world. Plus, it was written to allow efficient implementation. So efficiency is at the heart of MPI. It was recognized there's no point giving people functionality which looks useful but doesn't scale, wouldn't work on thousands of processes. Got a great deal of functionality. In principle, there's support for heterogeneous. In the early days, one of the models for MPI was you would run a parallel program across lots of computers in an office. At night, you'd go home and you'd turn people's desktop machines into a parallel computer. And you could have Windows machines, Unix machines, Intel processors, Sun microprocessors. In principle, MPI can run across. Now, in practice, nobody does that. People run MPI across 750,000 AMD identical processors. So the reason I mention this is some places MPI looks overly complicated. That is because in principle, it allows you to run a single program across a Windows machine with an ARM processor and a Linux machine with an Intel processor. In principle, in practice, nobody does that. But so first piece of code, because MPI is a library, you need to have access to the function prototypes. There's lots of magic numbers and constants and all kinds of things. C, C++, you hash include MPI.h. Fortran 77, you include MPI. I hope no one's using Fortran 77. Fortran 90, so you shouldn't, that's very outdated, don't do that. Fortran 90, you use MPI. MPI is a module, and I can see we have a lot of Fortran programmers. For technical reasons, there's a separate interface for Fortran 2008. Now, I'll come back to this later, but I will predominantly teach the Fortran 90 interface to MPI. There is a more modern interface which looks more, uses features which weren't in Fortran 90, such as derived types and function overloading. I have an example which illustrates how you would use the two. Now, there's very little difference between the two. I will teach the Fortran 90 interface because that is the most common. But actually, if you're a modern, very modern Fortran program, you like derived types and function overloading and such like, you can do that, but it's easiest illustrated with an example. Every MPI function has a prescribed format. All of them except for one or two return an error. So in C, you call error equals MPI, capital letter, lowercase letter, and the function call, and it takes various parameters. Now, C being C, you're allowed to ignore the error parameters. So you can just call the function. You shouldn't do this, but a lot of people do. The reason is that actually MPI's default behavior when it encounters an error is to crash. So actually, it would never, if there was an error, it would never return the error code. So that's C programmers tend to program in this way. For a C++ program, I'll come back to that at the end. Fortran, for some reason, Fortran programmers hate functions. They like subroutines. So in Fortran, you call MPI_x. It's a subroutine, and you have an extra error parameter on the end for the error argument. You can ignore it, but you have to supply it. Well, in the Fortran 2008 interface, because you can have functions with multiple numbers of arguments, you can ignore it. But in general, you have to provide it. So standard Fortran call MPI_x. The capitalization is not important in Fortran. Case insensitive, and you get an error code. So MPI is typically Fortran C neutral, but there's a few differences around the edges. So this is like MPI controls a lot of its own internal data structures. Okay, just so MPI. So there are lots of concepts in MPI, like groups of processors. Okay, which are quite a complicated thing. What MPI does is, if you want to define a group of processes, it just gives you something called a handle, which is just a variable. In C, they're type defs. In Fortran, they're integers. They're also user-defined types in Fortran 2008. It's better illustrated with an example, but the example I like to use is when you open a file. In C or Fortran, when you open a file in C or Fortran, that has an enormous amount of state associated with it. You know, where the file is, what its name is, where the file pointer is, all kinds of buffering and stuff. In C, you just get like a file pointer. In Fortran, you just get a unit number back. So you as a programmer just have to remember this single thing, and the C or Fortran runtime handles all the details. Same thing as an MPI. You often define quite complicated things. MPI just gives you, I think it calls a handle, which in C will be a type def. In Fortran 90 is just an integer, which you have to remember. This will become more obvious when we see an example. So our first real piece of code, you have to initialize MPI. Okay, it's a library. It's not part of the compiler. You have to explicitly initialize it. In C, the function is called MPI Init. Now this is the prototype. This isn't what you call, but it's a function called MPI Init, which returns an integer and takes two arguments, an integer pointer and a character triple pointer. Now, this is one of the first most unfortunate things about MPI, is that the initialization routine in C is ludicrously complicated. I will come back to that later. In Fortran, it's much simpler. You call Fortran doesn't by default have these command line arguments, or at least it didn't back in the Fortran 90 days. MPI Init I error. It must be the first MPI procedure called, but multiple processes are already running before MPI Init. So that's a common misconception. The multiple processes of your parallel program are created when you launch it, which we'll see later is through some command like MPI run. All MPI Init does is it makes them get together and talk to each other. Okay, so the program is parallel even if you don't call MPI Init. So what you do, a typical MPI program in C is int main. You have command line arguments, int argc, which is an int char star argv. MPI Init, you have to have a pointer to argc and a pointer to argv. So because argc is an int, this is an integer pointer, which we see here, integer pointer. Because in C, argv is a pointer to an array, it's already a double pointer. We pass the address of it, we get a triple pointer. Three stars in C isn't a record, but it's pretty serious. Now, in principle, that's there because you can imagine a system where only one process, rank 0, had access to the command line parameters argc and argv. So this syntax allows MPI to initialize the command line parameters argc and argv on all processes. But in practice, you often don't have command line parameters. You don't use them. Most parallel programs don't use them. So it's most MPI programs begin like this. It's perfectly acceptable to pass null. So most CMPI programs become int main void, MPI init null null. That's the standard thing to do. Okay. In Fortran, it's similar. You do call MPI init I error, where I error is an integer. Okay. Having previously included the header file or used the MPI module. Okay. So most C programs begin like this. Most Fortran programs begin like this. You can have code before MPI Init, but if you do any MPI calls, they have to happen after MPI Init, otherwise you'll get an error. Now, the most fundamental concept in MPI is a communicator. All communications, sends, receives, collectives take place within a communications world, which is called a communicator. It contains a group of processes. We'll see you can do sophisticated things in MPI. You can say, okay, I'm running my program on 100 processes. I want processes 0 to 49 to be one communications world, one communicator, and processes 50 to 99 to be another communicator. Okay, so you can do sophisticated things with communicators, but by default, we won't use it. We will just assume that all communications in principle involves all processes. There is a predefined communicator called MPI Comm World, which includes all the processes. So the fundamental point is, if ever you see an MPI routine which needs a communicator as an argument, and all communication routines take communicators as arguments. It's defining the world in which the communication takes place. Just put MPI Comm World. It's predefined. It's one of these predefined handles that will be set up in MPI, the MPI header file. So communicators are very general objects. They define the group of processes taking part in the communication. However, for the moment, just every time you see a communicator required as an argument, just pass MPI Comm World. So if you write a parallel program, if you run an MPI parallel, all the processes are running the same program. By default, they'll all do the same thing. Not very useful. We want to be able to say, if I'm process 7, do this. If I'm process 5, I want to send a message to process 6. We need to know who we are, and MPI calls that the rank. And there's a very fundamental routine in MPI called MPI Comm Rank, which says you pass a communicator. It takes two arguments. A communicator of type in C. So a communicator is a handle. So in C, it's of type MPI Comm. It's a type def type of, it's some structure which has been called an MPI Comm. And you get back the rank. Okay, your rank is your unique identifier, 0 to n-1. In Fortran, it's MPI Comm Rank. You pass the communicator. In Fortran, the communicator is by default just an integer. You get back the rank. By default, Fortran doesn't have this concept of pointers. It passes by reference anyway, so you just pass the rank and you get the error value back. Okay, so you cannot write a useful MPI program without calling MPI Comm Rank. So you have to call MPI Init, MPI Comm Rank to know who you are. It's not the physical processor number, it's a logical thing. When you run an MPI program, you're running on 10 processes. Those processes are numbered 0 to 9. Who knows where they're running physically, okay? It's not a physical thing, it's a logical internal MPI, but it is the most important thing. You need to know who your rank is so you can know who your neighbors are, who the boss is. You have to compute your rank. And traditionally, we call it rank, okay? That's just a convention. You can call it what you like, but the rank goes from 0 to n-1. This is going to kill the Fortran programmers. Fortran programmers count from 1. Let's be honest, the MPI library was designed, is a C library. It's written by C programmers. The numbers start from 0. That is it's a bit of a headache for Fortran programmers. You'll get used to it. But the ranks go from 0 to n-1 in C and Fortran. So how do we use MPI Comm Rank? Int rank. Call MPI Comm Rank, I have to pass a communicator. Let's pass MPI Comm World. We get the rank back and print hello from rank whatever. Okay. Or in C, in Fortran, insert IR, call MPI Comm Rank, MPI Comm World rank IR, write hello from rank. That is going to be the first program you write actually. But that is now you've got the processes printing out their rank. And although you've declared one variable rank, remember every process has its own variable rank. The rank will by definition be different on every process. Okay. The other thing you need to know is how many processes there are. Okay. If I've got this controller worker thing where I've got to send out data to all the other guys, I can identify the controller, say, look, if your rank is 0, you're the controller, fine. You need to send out messages to everybody else. So all you guys know to receive a message from rank 0, but I need to know how many people there are. You cannot write how big is the local road. If I have a big road, the size of the local road depends on how many processes there are. So you need to know how many processes there are, and MPI calls this the size. What you're actually doing is saying MPI Comm size says how many processes are there in this communicator. Okay. However, if we pass MPI Comm World, we're saying how many processes are there in the communicator, which contains all the processes. In other words, we're saying how many processes are there in total. So a standard MPI program goes MPI Init, MPI Comm Rank, MPI Comm size on MPI Comm World. Okay. So you would, instead of MPI Comm Rank, MPI Comm World rank, you do MPI Comm size, MPI Comm World size. Okay. How do you exit MPI? Well, you should call out finalize American spelling into MPI finalize. It must be the last MPI procedure called. It is not, doesn't have to be the last thing you do, but MPI is not it's not like OpenMP. You don't create parallel regions. You don't call MPI Init, MPI finalize. You call MPI Init at the start of your program. You run for 5 hours. You call MPI finalize. So typically in an MPI program, there isn't any code after MPI finalize. There could be, but You call MPI Init at the start, you call MPI Finalize at the end. That's it. Okay? You cannot call MPI Init again after calling MPI Finalize. So that's you do it once, you run, you do it, you finish it at the end. This is a bit of a technicality, but it's actually sometimes quite useful to know what machine you're on. If you're on a compute cluster, you'll be running on different nodes. They're physically different machines. Think about running a program across 10 different laptops. It's very easy, if you get things wrong, to run all the processes on the first laptop, rather than distributing them across multiple laptops. It's quite nice to know what the host name is. Now, MPI was written a long time ago, and for historical reasons, they called it the processor name. It's really the host name. But so there's a routine called MPI Get Processor Name, which has a slightly strange prototype. But this is how you use it. You declare an array of size MPI max processor name, or a character array in Fortran. You call MPI Get Processor Name. You get back the string, which is the name, and you get the length of the string. That's not relevant in C, but it is in Fortran, and you can then print it. So this could be a useful thing to do if you're running on a cluster which has multiple nodes, which are multiple physical computers. It's just a useful thing to do. If you run on your laptop, all your processes will print the same name. You'll say, I own machine desktop. But in a real situation, you're running across multiple laptops, multiple nodes. So that's just a little hint there. So the summary is I've covered some basic MPI calls. We've not done any explicit message passing yet, but it's enough to write, well, you could write a task file of independent jobs. If you had 100 files to process, you could launch an MPI program on 100 processes. They could all find out their rank, and rank 0 could process file 0, rank 1 could process file 1. But it's enough to get us launching and compiling parallel jobs. Now, MPI, just like the C standard, the Fortran standard, doesn't tell you how to compile a C or Fortran program. The MPI specification there's conventions, doesn't mandate how you compile it. So how you actually compile and run an MPI program depends on what machine you're using. Okay. So are there any questions about that lecture? The next lecture is very short. I'm going to talk about, and then we're going to do the practical, actually get you logged on and running programs. Are there any questions about that lecture? So you need to understand communicators. We have a predefined one called Comm World, which includes everybody. Every process is a member of Comm World. MPI Init initializes. MPI Comm Size tells you how many there are. MPI Comm Rank tells you who you are, and then you can finalize the program. So I would like to, yes, so there are, you can define your, so there are, we will see later on, there's routines to say, for example, split a communicator. You can say, take Comm World and split it into 2, or create a communicator which has ranks 7 and 8 in it. So we can do that. I only cover it briefly in this course, it's a bit more advanced, but we will cover some aspects. Yes, you can define your own communicators, but a simple MPI program just runs in Comm World. You can, most scientific and technical programs, at least until recently, just didn't exploit communicators. They just ran in Comm World. For various reasons, people are becoming more sophisticated, but you can write quite sophisticated programs just using Comm World. But yes, you can define your own communicators. So I just want to have a quick survey. Apologies that this wasn't set up before. How did we do? Okay, so we've got about a quarter of people on EPCC, my own Mac, my own Linux machine on a remote system. So that's so if you have a Windows machine, SSHing into us, so that's good. You can set up Windows. I have had students do it before through Virtual Studio, Microsoft Visual Studio. So that's useful to know. So only a third of you are doing the EPCC machine. So this covers MPI Cirrus and Arch, which are standard platforms. I've had to change it now to compiling MPI programs on Nextgen IO. So to compile programs on Nextgen IO, C programmers use MPI CC, C++ programmers use MPI CXX, Fortran programmers use MPI F90. That's quite standard. Now, I told you, and I do emphasize it rather a lot, that there is no such thing as an MPI compiler. This looks like I'm telling you to use an MPI compiler. These are not compilers. They're just simply wrappers which basically include all the libraries and the header files correctly. But the actual compilation is done by standard compilers. Here on the Nextgen IO system, it will be the GNU compilers. Okay, I'll show you a little. I have provided you with make files, which I'll point you to, which you can use if you want to do make. But we just use MPI CC, MPI CXX for MPI F90, and all they do is call on Nextgen IO, GCC, G++, or G4tran, but link in all the correct libraries and header files and to get the paths. So that's basically what they do. On Nextgen IO, we just run interactively. Now here we're just, if we were concerned about performance, we'd have to submit to a batch queue. If we've been running on Cirrus, I would have had a dedicated batch queue set up, but we don't. So on Nextgen IO, and this is 99% true probably on your laptop, you just do MPI run -N4 my MPI program, okay? It runs your code on 4 processes. There is a slight issue here that the output may be buffered. If your program crashes, you may see no output at all. When you're debugging, you may help. It can be a bit complicated. The problem is that one process might crash before the other ones and bring them all down and think, so that's the best, but it's just MPI. So basically it's MPI CC, MPI CXX for MPI F90 and MPI run -N4, run it on 4 processes. Okay, that's what we do. So that's really quite straightforward. I'll just show you the exercise sheets now, but the C++ interface, MPI is not an OO interface. It can be called from C++. Now, originally in the early days, they had different function calls. Okay, so for example, I'm not a C++ programmer, so apologies if my terminology is incorrect. But you know, you had the communicator with an object, and things like rank. The functions were method calls on the object. So you did rank is com.getRank, size is com.getSize. Okay. However, because the C++ standard, C++ is such a huge language now, the C++ interface is removed. Okay, so you can call C MPI from C++. It's totally, but the way that C++ interacts with C is well defined. Okay, so if you call MPI from C++, you have to realize that to C++, it's a C function. So you have to be aware. So you can't send objects and methods and, you know, things and template. It doesn't, what, you know, you can just send data. So as long as you know in C++ how to call a C library, the simple programs just work. Right? It's fine. But you know, you have to be careful. If you're interested, the Python interface, MPI for Pi, has kind of hijacked this. They mirror this thing. That's how the Python interface works. But anyway, documentation, the MPI standard is available online. There's a printed version. You can also use the man pages. We can maybe look at that on okay. There is a book which is very good, written by 3 of the people who were involved in the development of MPI: William Grob, Ewing Lusk, and Antti Skielum. I think you can buy it if you want. You don't have to. There's a lot of open source information, but it's a very good book. So the first exercise is Hello World. It's literally to write an MPI program that prints a message to the screen. The main purpose of this is to make sure you can get up and running. Okay. And in a classroom setting, I would be running around checking you can all get on. But what I will do is I will show you how to get on to Cirrus. Sorry, Nextgen IO. So I will, if you're doing it on your own laptop, we can help you, but I'll focus on those who are using the EPCC systems just now. So what you should do is, if I find the I'm sorry, I've lost myself a bit. I should have had this bookmarked, apologies. Fine. So what you will see is All the exercises are included in a single sheet, other than one or two at the end. So the MPI exercise sheet is there, okay? MPI exercises.pdf. So you might want to download that. It should render on the screen in GitHub, but you might want to download it. Now, what you cannot do in GitHub, for reasons which are utterly, I haven't explained to me, but they are totally stupid, is you cannot right-click and save as. Okay, you will not get the exercise sheet. So to get the exercise sheet, you have to click on it, and you have to click download. Okay. So whoever designed GitHub thought it was a good idea that right-click save as doesn't work, but there you go. So you can download that. So that's how you get that. That's your exercise sheet. So I will actually, if I open that in a new tab, so I have it up, we'll always have that. And the first exercise is, so this exercise sheet is generic. It has no platform-specific information whatsoever, or actually little platform. So the first exercise is to write a hello world program. Write an MPI program which prints the message hello world. Compile and run on several processes in parallel. Actually, I've said Cirrus here. We'll do it on Nextgen IO. And then modify it so that each process prints at both its rank total number of processes. So I'll do the first couple of bits just. The other thing is I don't provide much code here. I do actually provide solutions here. If you're interested, they're there. But I provided very little temp now. So this templates.tar includes now. So if I don't understand, if I copy path, is that how I do it? What I'll do is, so what I will do is I will show you how to go onto Nextgen IO. Okay, so what I will do, yes, so ready, yes, 99% sure on your own laptop it will be MPI CC, MPI CX90, and MPI Run. That is almost without doubt. So I will be using a particular, I'm using the Nextgen IO account number 1 as number 01, but you've got counts 10 till and up 10, 11, 12. So we do SSH minus XY. I'm ng guest 01, but you'll be a different one. And we have to go via a gateway Hydra VPN.epcc.ed.ac.uk. And the password is the password which I put on the chat screen, which I should try and get up. I think I have it written down. So we should be able to go. Now we're on this. Now we have to do a different thing. We have to do now. We have to go onto the actual machine. We do SSH minus XY next gen IO dash login 2, and it is the same password. Now I'm on. Okay. Now I need to get the code onto this system. Okay. If you look at the crib sheet, you'll see that that the way that GitHub works, because it does something really weird to the paths, you can't just, so the obvious thing to do is to go to the website. I find if I click on mpptemplates.tar, it's just going to download it to my laptop. I want it on Nextgen IO. So if I cut and paste the URL, I can wget it directly. Okay, that won't work. That looks like it's worked, but it won't work because I get the wrong. I've mentioned this on the sheet. You get the wrong URL from. Now you could download to your laptop an SCP to Nextgen IO if you want, but I think so. What we have to do is the URL we get from the website, we have to replace blob. So let's remove the MPP templates.tar because it looks like it's okay, but it isn't. We have to replace blob with raw for reasons totally bizarre. Okay, now I have the MPP templates.tar and I can unpack it. And it's very, very simple. I just have very simple programs in here, which are almost completely trivial. There's a hello.f90, okay? That's all it does, okay? I want you to edit this and put in the MPI Comm Rank, MPI Comm Size, okay? Or cat hello.c. Okay, but what we can do is we can do MPI CC, let's do MPI F90, it's more for MPI F90 minus O hello, hello.f90, MPI run minus n for ./hello, and I get 4 hello worlds. Now, I can't tell who they came from because I didn't say who the rank was, but that's the way you compile and run programs. Or I do MPI CC minus O hello, hello.c, and do the MPI run again, and I get the same thing without the leading space. If I want to, if you look at the C++, I'm not a C++ programmer, but I believe this is what you do. So hash include MPI. So that's my C++ is just C with printf replaced by C out. But let's just check that works. MPI CXX minus oh hello hello.cc, and we MPI run. So they all work. So they do all seem to work. I can see we've got a bunch of people on. That's good. So some of you are getting on. So so the only subtlety about the way we're distributing the source code is that I've given you a bundle, a tar file, which you unpack with tar xvf. But to get that onto, so if you're working on your laptop, you can just actually, I guess you can on your laptop. I guess you can just click on it and download it. Again, GitHub I found slightly bizarre, but what I shall do is I shall tell any questions here. So you could git clone the whole repository, exactly. So as Queven says, you could git clone the whole repository if you want to. That would be, so you'll just get the tar file. I haven't given the individual files maybe I should have, but so if you want to do that, we can just go to the, okay, this is the website. You just do clone or download, clone with SSH, we copy that, and then you do git, let's go, git clone. Oh, okay, I've already done that. Let's remove it again, sorry. Okay, git clone it, and it's cloning the whole thing, yes. Maybe it's the, okay, fine. So it worked with HTTP. Okay, fine. So maybe it seems to be maybe I did the HTTP. Maybe I did HTTPS before. But so, for example, here we have the exercises. I only have the tar files. Apologies for that, but I mean, you just need to unpack them with tar xvf, for example, mpp templates.tar. So I should maybe have provided them unpacked, but this is the first time I've used GitHub for distributing course material. It is much better than our previous system, which was via a website, but I maybe need to fine tune it. So please, if you're having problems on Nextgen IO, let us know. If you're having problems on your laptop, let us know, because we'll be able to screen share and we can solve them. I see that there are a bunch of people on, we have a dozen or so people on Nextgen IO. That seems to be working okay. So I will stay. I'm just going to grab myself another glass of water. But me and Queven is around as well. Thanks, Queven, for the suggestion about git clone. We will stay on the line till 1. to answer your questions. So it's really up to you. As I said, this is I've run these online sessions in various formats before. I've done them in sort of overloading the lectures in a double group and then a double practical. I felt that with the fact this being a 3-day course, it was best to interleave them. But so it's up to you. We'll be around. Please try the practicals, or you could just compile and run the solutions if you want. I will probably what I will do at the beginning of the next session is I'll spend 5 or 10 minutes going through the solution, because I know this sounds like a trivial example, printing hello world, but it actually surprisingly points out quite a few issues, quite a few important topics related to MPI. But the real meaning for the real purpose of this exercise is to make sure you can get on, log on, and compile simple programs. And even with just knowing comm size, comm rank, init, finalize, and get processor name, which is quite fun to play around with, you can write programs which run and show they're running in parallel.